Hi everyone, welcome to Mostly Math. Today we'll be discussing an important property of what's called the Schwarzian derivative, defined here as the operator s acting on a function f of z, where z can be a complex variable, though in this video it doesn't actually matter if it's complex or real, defined to be the derivative of the quotient of the second derivative to the first derivative minus half of the ratio of the second derivative to the first derivative squared. That's pretty weird, isn't it? Well, it has the interesting property where if you look at a Mobius transformation, which is defined to be m of z to be az plus b over cz plus d, so a quotient of two affine projections, or lines as they're called, where it has the important property where the determinant of this matrix is not equal to 0. We will actually derive this property in a moment. If we act on the Mobius transformation with the Schwarzian derivative, it satisfies the fundamental property that s acting on m is actually 0, or s will annihilate m. Basically, this is used in complex analysis for a variety of different purposes where you want to map a section of the complex plane to a different section. We're not going to be considering that in this video. We're just going to be considering z to be a complex variable. It could be real. It doesn't matter for this video. And let's get started. First, we have to derive a second important form of the Schwarzian derivative. All right. The second form is derived as follows. Well, obviously we have a prime here at the top. We just want to actually take the derivative of that first term and see what we get. Using our product rule, f of g prime, f prime g minus f g prime over g squared from high school, of course. This first term is actually going to be f double prime, triple prime actually, f prime minus f, which is f double prime here, g prime, which is f prime prime, f double prime, over f prime squared. That's the first term. We still have this other term here along for the ride. Simplifying this first term here, it's going to be f triple prime over f prime. Awesome. Minus, we have f double prime over f prime squared. We also had half of it here. So the whole thing just becomes, we got negative 1 plus 1/2, which is minus 3/2. Go ahead and write down our final result up here. It's just going to be f triple prime over f prime, no parentheses needed, minus the unusual looking 3/2, which we see where it comes from, f double prime over f prime squared. Interesting, isn't it? Yeah, it's pretty unusual. Let's make sure I have it right. Yep, it is right. So now we can just proceed with the calculation of the Schwarzian derivative acting on a Mobius transformation. We'll need the product rule again in a second. I shouldn't have erased it. Let's put it back. All right, now we're going to look at a Mobius transformation. We obviously have to take first, second, and third derivatives of the Mobius transformation to plug it into this expression. So let's just start taking derivatives and see what we get. M prime is going to be just a straightforward application of the quotient rule here. Going to have f prime, which is going to be a times the bottom function, cz plus d, minus the derivative of the bottom function, which is just going to be c times the top function. And this is over cz plus d squared. bottom function. Well, we see an interesting thing is actually going to happen here. The subsequent derivatives will actually simplify since these two terms cancel, since this is ACZ and so is this. So we have just the constants being subtracted. Becomes AD minus, see, I made a mistake here. I wrote a D instead of a B. It's pretty important. AD minus BC over CZ plus D squared. Fantastic. This is the first derivative. And we see that taking the second and third derivatives is going to be easier since we no longer have to use the quotient rule. So, second derivative, well, it's just going to be, I guess I can take the second derivative down here and put the third derivative up there. Doesn't really matter. Second derivative. Okay, we have the AD minus BC going along for the ride. And when we take a derivative of something like 1 over z squared, just going to be minus 2 over z cubed, of course, with the additional complication that the chain rule requires us to differentiate the bottom function as well, becoming minus 2c over cz plus d squared. Pretty cool. Notice the additional cool thing, however, it is related to the first derivative. We can simply write this as minus 2c over cz plus d times the first derivative. This will simplify our calculations momentarily. Computing the third derivative now. See, I'm going to be out of room to do the final calculation. I don't know where I'm going to put that. Don't know where that's going to go. Up here, I suppose. Okay, the third derivative is simply going to be the same thing that we had before, and we obviously just have to differentiate it again. When we do that, we're differentiating something like, I should have put the 3 down here. Differentiating something like 1 over z cubed, which when differentiated is simply minus 3 over z to the 4th. So we have the same thing as before, minus bc, got the minus 2c, now we have the minus 3c over cz plus d to the 4th, which just simplifies as 6c squared over cz plus d squared times m prime, since we have an additional factor of c and so forth. And now we are going to see why we went through all the trouble to write it in terms of m prime. Let's actually calculate s acting on m of z. Well, when we do that, looking at this section here, we see that the first term is something like m triple prime, too many lines there, m triple prime over m prime. And since we already have it written in terms of the m prime, we can just cancel that out and write the result immediately. 6c squared over cz plus d squared. And the next term, minus 3 halves. And this is going to be, just looking at the ratio, m double prime over m prime. Obviously, the m prime is going to cancel out, just going to be minus 2c over cz plus d. We do this, put it up here, has to be squared. And we get something rather curious. We see that we can actually factor out the 6c squared over cz plus d, so pretty much everything. This is squared. Constants are just going to be, I'm not going to actually factor out the 6 yet, since we don't know that it factors. It's going to be 6 minus 3 times 4 over 2, which happens to be 12 over 2, which is 6, of course. So the result is 0, verifying my claim. So I think this shows us, in fact, I've shown you that it shows us that if we act on a Mobius transformation with the Schwarz field derivative, the Schwarzian derivative, not to be confused with the Schwarzschild from general relativity, which I'm also studying now. There's too many Schwarzes going on here. But this tells us that if we act on the Mobius transformation with the Schwarzian derivative, it's going to be 0. You might ask, what is the utility of this? Basically, you have to study complex analysis. But if I had to give you a simple example, let's say we had some function which had like exponentials up here and exponentials of something else down here, which probably had logs in it, which eventually simplified to be this form, but you just didn't know the identities to simplify it. Well, you could act on this weird function with the Schwarzian derivative so that it's 0 and be like, there has to be something I'm missing, has to be some kind of identity which can reduce these transcendental functions to a rational form. That's what I got for you. If you enjoyed this, want to see more math, please subscribe to my channel. Talk to you next time.